Okay, so today for the analysis seminar, we're happy to have Sanchit Chaturvedi from Stanford. Sanchit was a Courant undergrad a few years ago, and then he went on to Stanford. And he is talking about the Vlasov Poisson Landau equation in the weakly collisional regime.
Thanks, Scott, and Vlad for inviting, and everybody else for coming. It's very nice to be back virtually and seeing very familiar faces. Okay, so well, the structure of the talk is essentially I'm going to give a very brief introduction to what kinetic theory and what equations I use. Then I'm going to talk about the entropic dissipation, move on to phase mixing, then try to combine these two effects, and finally give like very brief proof details. Okay, so for the purposes of this talk, we will have a density function f, which depends on time, space, and velocity. And it captures a mesoscopic description of the gas particles. So essentially, it's not the gas, like the microscopic description or not the fluid description. And for this talk, I will be on a torus or in 3 dimensions. But the velocity will be on the whole space, R3. Okay. So the simplest model one can try to consider is a transport equation. The point is you just free stream without any additional force. Okay, and the other model that I will also consider is the Vlasov-Poisson model. This is for the collisionless models, and in this case you have like an extra mean field effect, which is through self-interaction and is given by this electric field. Okay, so I will come back to this in a bit. Now, for collisional models, I have for this talk it will mostly be Landau, but you could have the QFF could be Boltzmann or like basically a lot of other things. And I will focus on Landau with Coulombic potential. So one thing to note is that this is a second order operator. It's degenerate because of phi, but I will come back to it in a bit. And by the way, feel free to like object or ask questions. Right. Now, for a realistic description of plasmas, one would, in theory, like to account for both the collisional and the mean field effects. And so we will also consider, or the main object of this talk will be the Vlasov Poisson Landau system. So here is Vlasov Poisson, and here is the collisional interaction. And for realistic situations, you want nu to be very small, of the order 10 to the minus 30 to like 10 to the power minus 2. And this is what I will look at. Okay, so now let me talk about what collisions do or how do they behave. So there is this very well-known age theorem for collisional models. And essentially what it says is your entropy always decreases. So this is the first one. And it's zero if and only if you have, if it's a local Maxwellian at T and X. And here, rho, theta, and u are essentially fluid variables. Okay, and so this is also known if I'm on a torus, this density temperature and the fluid velocity are all constants, independent of x and t. So in the limit as time goes to infinity, we expect that we will converge to the global Maxwellians. Okay, so and this has been studied for a while now, and this like it was started by Guo essentially in 2002 for Landau. And the theorem is if initially you are close to a global Maxwellian in some appropriate weighted norm, then the unique solution is global in time and converges to the global Maxwellian. So I only highlight 2 things. I mean, there's like a very rich literature, but let me just highlight 2 of them. This is Guo in 2002 did it for Landau equation, And in 2012, Go did it for Vlasov Poisson Landau equation. Okay. So what is the idea? I gave a very brief idea of the proof. The point is you just linearize around Maxwellian. So the Maxwellian we use is just this. We normalize everything to be one, or appropriately to get this this global Maxwellian. Then the equation you get is, well, transport. You also have this linear operator coming from the linearization, and this and n is the nonlinear term because of QFF, essentially. So now the basic idea is to use energy estimates. You multiply by F and integrate in X and B. And in theory, what we would like to do is use the fact that LFF is actually bigger than delta times some norm of F. So this is something we have to figure out what norm it is, and also control the nonlinearity by essentially the L2 norm of F and this norm that we will have to cook up. Now there is an issue. This is not necessarily true, and you need like well-designed energies, because there is a weight loss issue for the Landau operator, and this has to do with the fact that this phi was actually degenerate in velocity, or it's not degenerate, but it's I guess it's different in different directions. Anyway, so then what you need to do is you need to incorporate different velocity weights, and you also have to take derivatives because it's a nonlinear problem. And finally, L also has a kernel which needs to be treated separately. Okay, I'm not going to say much more about this. And I will move to phase mixing now. Are there any questions on enhanced or entropic dissipation?
Can you say something about that norm where you had the lower bound for LF, F?
Yeah, so, okay, yeah, so the point is if you remove the kernel, then you have this lower bound. So like, let's say you can write, let's see. So I want to write F as this. Do you see what I'm writing, by the way?
Yes, yes.
So let's say P is the projection on the kernel. Then what you can say, I think, is LFF is bigger than, well, this I minus PF in some weighted norm, sorry.
Okay, so you have some power laws involving V, and maybe you have some kind of Gauss.
Yeah. So the way this works is what you need to do is you need to penalize when you take, at least for Lambda, what you need to do is you need to penalize when you take partial V derivatives, for example. So basically, the weight function you have to consider is something like, I don't know, let's say you the total number of derivatives you take are 10. So then you need to take something like this, where beta is exactly this.
Okay, so that's how you define your Sobolev norm.
Yeah, so yeah, exactly. So for every derivative you take, you have to penalize it.
Thank you.
And you're missing a square on the the right hand side of that inequality, aren't you?
Oh yeah, you're right, of course.
Okay.
Yeah, and also here. Thank you. Okay. Any other questions? Okay, if not, then I'll move on to phase mixing. Okay, so this was discovered by Landau. What he discovered is a linear relaxation mechanism for transport equations. And what's interesting is, well, first of all, you don't have a change in entropy, and the second thing is you don't have dispersion because you're on a bound. You're on a torus, for example. Then, so one way to think about this is that the transport operator pushes information from lower to higher velocity frequency as time evolves. And for the linearized equation around this Maxwellian, for Vlasov-Poisson, you have a convergence in the long time limit to a transport equation. Another way to say this is that the mean removed density, and this is how you define it, this converges to 0 in the limit. And this is referred to as Landau damping. I mean, so there are other ways to say this. You have weak convergence and everything, but let me not go into the details. Okay. All right, and this is a picture that I just took from Villani's notes. So the point is, let's say you have initial disturbance at time 0. This is the red line. Then what the transport operator does is it will essentially shear it in some sense. So at time 1, you get like a slant, and then this keeps on happening. So at time 10, you basically have mass everywhere. And what this means is you kind of homogenize. And so right, and so the point, and then what you see is, since when you integrate in velocity, you should look the same on all of these black lines when you integrate in velocity.
Sanchit, you're going too fast for my brain to keep up. Can you go to the previous slide? So yeah. I want to slow you down a little bit.
Sure, thanks.
So can you explain point 4? Another consequence of phase mixing is that. Can you explain that again?
The density converges to 0.
Yeah.
Yeah. So let's see, how should I say it? So this is, I mean, that was more like a throwaway remark, but anyway, so since you asked me, I'll say it. So this is what the equation looks like. The Vlasov-Poisson. So what I'm saying is, in the limit, what you want, so let's say f sharp is the limit, then what I'm trying to say is that the f sharp satisfies some sort of a transport equation. And one way to think is that this goes to 0 as time goes to infinity. Where, I guess, and the damping comes from the fact that E goes to 0. And E is exactly as well. E is this. Let's see. I think it's gradient inverse of this difference. I don't know if that makes sense.
Yeah. Okay. Yeah. That's fine. Keep going.
I'll come back. I mean, so when I discuss this thing with Villani, I'll try to say more about this. Okay. Oh, so this is okay. So I guess maybe from the picture it's a bit more clear, because when you integrate on along these lines, they should all look the same. This essentially f dv for every x, and when you take the gradient, it should kind of converge to 0. Okay, so now then you can ask the question for the nonlinear problem. So do we still have Landau damping or not? And this was done was somewhat recently in the great paper of Villani. So what they say is, let's say you're initially close to the Maxwellian in an analytic norm. Then you have exponentially fast convergence to f sharp, where f sharp solves the transport equation, and the mean removed density converges to 0 exponentially fast. Okay, so I also want to say that there has been a lot of work after that by Bedrossian, Masmoudi-Muo, and Grenier, Nguyen, and Rodniansky, where they made the argument much smaller, and also included the Gevrey, like they also included that you can have Gevrey norms, for example, till Gevrey 1/3. Okay, and so implicit damping for fluid models, for example, for shear flows, is also related to all this stuff, and there has been a lot of work, thanks to the works of Jacob, Tarek, Pierre, Emmanuel, Nader, Toan, and Vlad, Faye, and Michel Coty-Zelati. And personally, I don't know very much about this, so I will not say anything more unless there are questions. Okay, so now one question one can try to ask now is, we have nonlinear Landau damping for analytic algebraic norms. Can I ask the same question for, let's say, Sobolev data? And this was, so you see these plasma echoes, which was seen by physicists and also in experiments a long time ago, in I think 60s or even earlier. But only recently, Bedrossian proved that actually there is some, you have some obstruction to proving Landau damping. And this is essentially because because of this nonlinear interaction of waves that happens periodically in time, for example. Okay, so I don't pursue this any further. And if there are questions on Landau damping, I can try to answer them now. Otherwise, I'll try to combine these two effects together in the weakly collisional regime. Okay, so again, what I'm going to look at is Vlasov Poisson Landau system with weak collisions. And this is Vlasov Poisson, and this is the Landau part. So what we expect is, we expect that Landau damping should give us relaxation for small times, as in depending on nu. And the collisional effects only kick in at a much later time, depending on nu inverse, for example. I'm not saying how it depends on nu inverse yet, but I'll talk about it in a bit. So the point is, you have two of these effects which I want to use. So one of them is Landau damping, and the other is entropic dissipation. And I want to combine these two in some way. So now one can already ask, what can we prove with that has already been in the literature for a while? And so the best, I think, is what one can say is by Nguyen. So what this says is, let's say you are close to a global Maxwellian with appropriate weights again, in a Sobolev norm with the size of the perturbation is dependent on nu linearly. For example, it's epsilon times nu. Then you have a global in time solution, and it converges to the global Maxwellian with this specific rate. So it's some sort of a stretched exponential. Okay, so let me say something about this. So Nguyen's method only allows you to understand dissipation coming from the collisions, and as a result, the time scale is analogous to what you expect from heat equation. Exactly being that this only helps you when time is bigger than nu inverse, for example. But when nu is very small, as I said, there are two more mechanisms that are working. One is phase mixing, which we've already talked about. That should give you a nu independent decay at times of size 0.1. And the other one is enhanced dissipation. And the reason why we have this is because transport part moves the solution to a higher V frequency, and then the collisions just are more efficient at damping stuff. Okay. Now, so what we expect is, if we understand these two things together, then we should be able to say we should be able to give a similar theorem as Nguyen, but for larger perturbations. For the initial norm, I mean. Okay, and then Bedrossian successfully did this and understood the two mechanisms for the nonlinear Vlasov-Poisson-Fokker-Planck. Okay, so let me just show what the equation is. So the point is, you have you again have the Vlasov-Poisson, and the nonlinear collision operator now looks like Fokker-Planck. And they also have the density rho bar, which makes it nonlinear. Okay, so then let me not talk about the model too much and give you what he proves. So what Jacob proves is that there are no echoes, and further you have enhanced dissipation. And this is exactly like a very rough version of what he proves. He proves much more, but let me just give this. So again, if you have initial, so let's fix M and N large enough. And then if you have initially you are small, if you're close to the global Maxwellian in an appropriate weighted norm, but note that the initial, I guess the perturbation now you can allow for nu 1/3, for example, as opposed to nu from Nguyen. So what he proves is, so here F0 is the zero mode for in the Fourier decomposition in X. So what he proves is that you actually are bounded by nu 1/3, and then you also decay like what you expect from the heat equation. What's the interesting thing though is if you remove the zeroth part, or the non-zero modes actually decay faster, and this you can see just that for time bigger than nu minus 1/3, you actually this exponential is helpful, as opposed to time scales of nu minus 1 from Nguyen, or even this one, for example. And finally, this mean removed density, you can also get the new independent time decay. So this captures both enhanced dissipation here, and you also capture Landau damping here. Okay, are there any questions? And again, Jacob proves way more than this, but I'm just giving like a very short version of what to expect. Okay, so now, again, because of transport, the decay is much faster for the non-zero modes than what you would expect from the heat equation. So now, Jacob has to rely heavily on the exact structure of the linearized equation. In particular, he inverts the linearized equation via a Fourier transform, and the reason is because he only sees partial V, or Laplacian V, partial V, and V partial V. So it's possible in that case. But doing the same seems somewhat challenging for the linearized Landau operator. It could just be that, okay, that I might lack the necessary tools to do it from a Fourier perspective, but okay, anyway, it seems scary. So what the issue is that the linear operator L is actually variable coefficient with velocity waves, and they're also anisotropic because exactly of this phi. Let me just write down phi again. So it's different in different directions. Okay, so as a result, we have to rely on techniques that allow us to control the linearized equation without using explicit formulas. Okay. So now let me compare, which I've already done, but let me just say it again, compare Bedrossian's work with Nguyen's work. So the main difference, or one of the main differences, is that he can actually understand enhanced dissipation, and as a result, the collisional term kicks in at a much earlier time, which is nu minus 1/3, as opposed to nu minus 1, that Nguyen's method suggests. And okay, second of all, he also understands Landau damping. So what that means is one can try to understand what Moore-Villani techniques would give us, let's say for size or data of size O epsilon, and in a sufficiently regular Sobolev topology. What they say is you can control your flow till time on epsilon minus 1, and hence and as a result, Bedrossian can treat as a data of size O nu 1/3. So what I'm saying is, since your collisional term kicks in at nu minus 1/3 time, and you can control your electric field or your collisionless terms up till time of O nu 1/3 or O nu minus 1/3. So then that means that you can actually control everything for data of size O nu 1/3. Does that make sense? And the other thing is, yeah, so the Go has to use data of size O nu because he doesn't understand enhanced dissipation or Landau damping. Okay, and finally, Jacob uses the density estimates to close the problem, and this is exactly where he has to basically use the exact form of the linearized operator. And what he does is you can explicitly incorporate this in the semigroup. And finally, for linear Landau operator, we can't do this, or at least we cannot. So we just use an approach entirely relying on energy estimates. Okay, so let me just mention our theorem, and this is joint with Jonathan Luke and Toan Nguyen. Jonathan's at Stanford and Toan at Penn State. So what we say is, let's assume you have enough derivatives, which would be like at least 11, and you are initially close to the global Maxwellian. Then if you oh, I think I'm missing an exponential here. Anyway, so what I'm saying is, if you're close initially to a global Maxwellian in an appropriately weighted norm, with again the same nu 1/3, epsilon is independent of nu. Then first of all, you have energy boundedness. So what that means is when you take derivatives in the same norm, you can bound it by initial data, like essentially by initial data. Well, I should also mention that Y is this vector field, T partial X plus partial V. Okay, so that's the first thing. The second thing we prove is you have energy decay, in the sense that, so let's say omega is 0. So I'm just writing it for the lowest order derivatives. That the 0 mode again decays like nu T 2/3. This is what you expect from Guo. But if you remove the mean density, then you decay. You actually decay faster, or you decay on time scales. You decay faster in the sense that it's nu 1/3 T, but you take the power 1/3 instead of 2/3. The reason is a little technical, so I will not say much more about why this happens. But the last thing we understand is Landau damping. So what we can say is, well, first of all, you have, so M max again is at least 9. What I can say is that the mean move density, you have nu independent decay. And you also have exponential decay for the same thing. But again, the exponential decay comes in at the time scale nu 1/3. But it's again a stretched exponential with the power 1/3. Okay. Are there any questions on the Steppenwolf theorem?
So the new independent decay that you get on the densities, non-zero mean, this M max, is that just because you've chosen to include only so many vector fields, or why is it limited?
Wait, what do you mean? So I mean, yeah. So you mean instead of M max plus 2, you mean?
No, I mean,
Also, yeah.
Can you prove that you get algebraic decay of any rate whatsoever?
So I can't prove it unless I assume something on the initial data, if that's what you mean.
So you would need to assume infinitely many derivatives on the initial data. Okay, that was my question.
Yeah.
But if you do that, then it just works.
Right, yeah, exactly. So this is similar. Oh, this is in some sense similar to what Jacob does, because he also assumes like some finitely many derivatives, and then you can prove, depending on these derivatives, how much, like you can get some amount of decay. But somehow at the top order, it's the only issue is at the top order, for example. But at the top order, you can essentially use, what ends up happening is you can actually use collisions instead of what you expect from the invested thing. I don't know if that makes sense.
It does.
But yeah, okay, thanks. But I'll come back to some details in a bit. Are there other questions? Okay, so again, the collisional term kicks in at time nu minus 1/3. And so now note that partial V does not commute with the transport operator. So what I'm saying is partial XIF, you can write down the solution explicitly as x minus TV initially, minus comma V. So when you take the partial V derivative, you also hit partial X. So you end up gaining a factor of T. But from the theorem, okay, let me go back to the boundedness statement. I can multiply by nu to the power beta over 3. Beta corresponds to the number of V derivatives I take. And then I can take care of this time growth essentially. So one good dictionary to keep in mind is that 1 plus T, or T essentially corresponds to nu minus 1/3. So basically every time you take a partial V derivative, you have to supplement it with a nu to the power 1/3 weight. Okay. Secondly, the velocity weights are chosen exactly as Go has to choose them to close the energy estimates. And this explains the n minus 2 alpha minus 2 beta, for example, in the initial data. And finally, the vector field Y, which I again write here, this is used to capture Landau damping from the transport operator. And I will mention this in the proof details. Okay, finally, enhanced dissipation we capture using hypocoercivity in the density estimates, or sorry, in the energy estimates. And also we also need density estimates as Jacobni's and also Muavelani to actually close the problem. Okay, so now I'm going to move on to some proof details if there are no other questions. All right, so let me give a very general overview of what the strategy is to prove boundedness. I'm not going to talk about the exponential decay at all, but so the idea is you need to prove energy estimates and density estimates basically in parallel. So to close everything, I need to understand, well, first of all, hypocoercivity, which is just to understand enhanced dissipation. And secondly, I need to commute with these vector fields Y, the other vector field partial V and partial X. So these are the 3 vector fields I use. Again, Y is used to capture Landau damping, and the other ones are, you need them to just close the problem as Go has to. And finally, I need density estimates. So the reason I need density estimates is to actually control these terms, which are the ones that you get from Vlasov-Poisson.
So if you were to ignore the electric field, you wouldn't need to propagate this density estimates?
No, yeah, exactly right. And what's also interesting is actually if you don't have electric field terms, then you can close the problem at, so let me say this, without E terms, the initial perturbation could be of size O1. Oh, okay, it's little O1, so O epsilon, let's say.
That's actually a good thing to say.
Yeah. Okay, so now let's look at density estimates. So what do I need to capture? I need to capture Landau damping here. So I'm not talking about the exponential decay yet, because what we do is we close the problem first, we prove boundedness, and then go back to prove exponential decay. So here we just need to understand Landau damping. So what goes in to do that is, well, first, usually what you do is you need to control the linear flow, and the linear flow looks like this. Okay, okay, let me write down H instead, because this would be the density. This is the linear flow, where L is either for our case the linear Landau operator, or for Jacob's case is the Laplacian. But you also have the other stuff for Jacob. For us, it's just L. So because I don't want to invert it, so basically I don't want to take a Fourier transform in V. What I do is I again do an energy estimate. But this energy estimate is for linear flow. So to understand Landau damping and close everything, what I again need to understand are two things. I need to understand hypocoercivity, but this is for the linear flow. And also I need to understand Landau damping, which is what we need to understand anyway. And this I do by commuting with Y. And finally, to actually do everything, I also need to do resolvent estimates. To invert this linear, to invert the linear operator. Okay, so the idea is like you have an overarching main energy estimate, but in the density estimates you also have a nested, like a mini energy estimate. And this energy estimate basically allows us to control, or allow us to get the Landau damping. I'll talk more about the density estimates in a bit. Are there like questions on the general overview?
I have a quick question.
Uh-huh.
Yeah, so having to do with this point little b. So to capture the Landau damping, all right, so you're on the torus, right?
Yeah.
So this is not, right, normally, okay, if I were on the whole space and I wanted to prove a dispersive estimate, I might use these Y commutators, right?
Yeah.
But you're telling me that on the torus to capture a mixing effect,
yeah,
it is also working well.
Yes, that's what I'm going to show you next. And
Awesome.
No, that's a great question. I'm going to suffice it. So I think it suffices to show only for transport operators. Okay, so let's look at transport. And I claim once you understand everything for transport, then with a lot of work and a lot of frustration, you can actually try to do it for the other case. But let's look at transport. So what's the first thing? So again, Y is T dx plus dv. And you can check that Y actually commutes with transport operator. So what that means is you can take as many Y derivatives as you want, and Y omega F also solves transport. Okay, so now you can do an easy energy estimate because Y omega F satisfies transport. You can say that Y omega F at any time t is bounded by the initial data. Okay. Now this is where the what you asked me is actually, this is where you have. For technical reasons, let me say that you also multiply by e to the power minus v squared in the density now. So this is how I define my mean move density. So F is being multiplied by an exponential weight. And what I'm saying is, what I'm saying here is that because you don't have a zero mode, you can bound this by partial x, L2x. This is exactly t dx 1 over t. Well, okay, I haven't really done anything yet. Okay, and now because rho is independent of v, this is also t dx plus partial v of mean move density. So this is how the y shows up. This is exactly y. So okay, let me erase it and actually just write down y.
So you use a Poincare X, which exploits that you're on the torus.
Exactly. Yeah.
I see. That's cool.
Yeah. Thanks. And now what you do is, well, okay, this is 1 over t. Well, in some sense, you can just put it here. So this basically is you can take the density for y rho, and now you can use basically, because rho is defined with this exponential weight, you can use like a point or a Cauchy-Schwarz in V to get this yf L2x L2v. And okay, so once you have that, then you can just use the energy estimate, the first energy estimate, to show that the density actually decays like polynomially in this way using y. So what I've done is I've only understood Landau damping for transport, but using y. So of course you can take the Fourier transform and try to understand this. You can get like exponential decay, but I can only, or at least what I do now, I can only understand polynomial decay, but as much as any polynomial that I want.
And when you say y to the omega applied to the initial density, that's really just dv to the omega, right?
Yeah, you're right. Yeah.
Okay.
Yeah, because it just, yeah, right.
I guess I'm confused. I guess I'm confused as to why you can't get exponential if your data were analytic.
Oh, I guess you can, but then you would have to like understand the constants which I have suppressed.
Yeah, and that's always a pain. Okay.
Yeah.
All right. Cool.
Yeah. I mean, if one is able enough, they can try to get it.
Yeah, or persistent. Yeah.
Yeah, exactly. All right. So does that make sense for transport? Okay. Now let me talk about hypocoercivity. So the idea again is that transport operator speeds dissipation up by basically messing things around. So for concreteness, I will only consider Fokker-Planck, and okay, for the linear Landau, you can do the similar things, but it's more painful because you have to understand the weights and everything. So let me suppress that. So what I do is you take derivatives in partial v, and because partial v does not commute, you actually end up getting in this term minus partial xi f, where just partial xi just shows up because of the commutation. Then if you consider the time derivative of this quantity, you actually get a nice coercive term. Well, okay, now that I'm taking derivative, I don't actually have these. But because you multiply by partial xi here, you multiply by partial xi here, this gives you the nice coercive term. And I want to mention that there is an alternative approach to understanding this kind of stuff using Hormander's hyperellipticity by Scott and John Christoph, who are also in the audience. Okay, but I don't know very much about this, so I'm not going to say anything.
Wait, sorry.
But, yeah.
So the Laplacian gradient of df, when you multiply by gradient xf, what do you do?
Yeah, that's a good question. I mean, so what you need to do is, what you end up doing is you have to do three things. You have to get energy estimates for f. So this is where you just multiply f by this equation. So this gives you one estimate. The other one you need for partial xif. The third one you need for partial vif. And the fourth one is exactly this cross term.
And you're using the dx commutes with dx.
Yeah. So then exactly. So then that term you can try to control with the other two, for example.
Okay, so I'm going to be that guy. I'm going to bog us down in details for a sec, but it's just because I really want to understand.
Sure.
Because it's interesting, right? So, okay, when you build your new norm, this is a computation I should do for myself probably. But when you build your new norm, you have alpha, beta, gamma.
Yeah.
And you're saying you can optimize those to get the nu to the 1/3.
Yeah, that's what I'm going to say next. But thank you.
Okay.
Yeah. So that's exactly as I said. if you can, this is the norm I consider, and I guess this would have answered Blas's question too. But this is the norm that I would consider for A, B, C, and D. They're appropriately chosen. And again, if you just choose them to be large enough, then you can see that this cross term can be absorbed by, for example, 1 and 2. So this is a good norm, for example. Then, as Dallas asked, well, let's say I replace the Laplacian by nu times the Laplacian. Then what we have to do is we have to choose A and B independent of nu, but they have to be large enough. This largeness comes from, okay, whatever the constants you get from Landau and all sorts of other things. But you have to choose your C to be nu 1/3 and D to be nu 2/3. And this is exactly where the dictionary comes in the fact that when you take partial V, you have to allow for T growth, and that just amounts to multiplying by nu 1/3, for example. Does that make sense? Yeah. Okay. Okay, yeah, so this is, I'll just say it again. So then this exactly is that nu 1/3 should cause, or nu 1/3 amounts to like nu 1 plus T growth. Okay, so now what I want to do is I want to combine these two effects. I want to combine hypocoercivity and I want to understand Landau damping. So what I can do is I can try to do, I can try to prove energy estimates for y omega f using hypocoercivity to understand both of these phenomena. For the Landau equation in the weakly collision regime, it is enough to just do energy estimates for the commuted f, and you can actually get phase mixing and enhanced dissipation for initial data of size 01. This is what I said earlier. But the electric field terms, which are, for example, the linear term or the nonlinear term, in the Vlasov Poisson Landau, they pose a lot of additional issues. And this is exactly why I have to consider data of size nu 1/3, as opposed to size 01, which you can do for Landau. Okay, other questions? Good, okay. So let me just give again an overview of the strategy. So what I will do is I will prove both density and energy estimates, and I will prove energy estimates for the commuted F via hypocoercivity. And this allows me to understand enhanced dissipation, and y will let us prove Landau damping. And to control the E terms, we will perform density estimates separately, where we follow a usual Duhamel approach, but the solution semigroup will contain the linear Landau operator. And I will not explicitly invert it, so we use energy estimates again to understand this linear flow. And finally, we have to understand both enhanced dissipation and Landau damping for the density estimates too. And this, again, so essentially what we do is we do this energy estimates, the main energy estimates again, essentially, to understand hypocoercivity. And we use Y to get the decay, the new independent decay. And I'm going to mention, I'm going to give a little bit of a flavor of what goes on in the next slide. So when I linearize around the Maxwellian, the equation I get is, okay, you have the usual transport stuff, but you also end up getting a linear term from E. You have the usual nonlinear term, and you also have this nice coercive term from the linear Landau. Okay, you also have the other terms, but let me just suppress everything in the nonlinearity end for now. And the linear Landau kernel is this thing. Okay, this doesn't say anything, but what one should think about is it's like a second order operator of essentially of divergence form, where sigma ij is defined to be okay, this is not A, this should be phi ij. You convolve the matrix, the collision matrix with mu. So what that means is sigma ij essentially depends on V, for example. Other questions? Okay, if not, then now what I do is, again, I don't want to take Fourier transform in V, but what I can do is I can take Fourier transform in X, which commutes with L, because L is only dependent on V. So one can check that this is what the Fourier transform of mode K will satisfy. Okay. Now, let's say Sk is a solution semigroup of this equation. This is the linear Landau flow. Then I can use Duhamel to write down what f hat k should satisfy. This should be the initial data term. This linear term and also the nonlinear term. So as so now I will multiply by square root of mu and integrate in V to get the equation for density. Okay, this should also depend on X. Okay, so this linear term, the first term gives us this. Basically, you're integrating the same mode against some kernel. This kernel is similar to what you would get for Vlasov-Poisson, for example, or the linear Vlasov-Poisson. It also depends on nu, though. So this is where most of the work to invert this linear operator, we have to do some resolvent estimates. So I will not mention anything about it, but this requires some work as well. And here is you're flowing under the linear Landau flow, you're flowing the nonlinearity here. The first term is somewhat easier to understand. So let me let me just say what I can get using. So what kind of decay statement I can get when I flow under Sk. Okay, again, you don't know the exact form of Sk. So what we do is we use energy estimates and appropriate Y to capture phase mixing and enhance dissipation. So now here, this is where I use energy estimates for linear Landau flow. And what I do is I need to understand two things. I need to understand Landau damping, which gives me new independent decay. And here I will use vector fields, which are of this form. So if eta is 0, this exactly is the Fourier transform of our Y, which we had t partial x plus partial b. But I will also need, because of the nonlinear terms, I will need eta to be non-zero. Anyway, I'll talk about, I probably won't talk about it, but anyway, we do need it. And I need enhanced dissipation to give me new 1/3 T decay instead of just new T decay, which you would get from the GUO estimates. Okay, so then again, Y eta n, this is possible because Y eta n commutes with the transport, as I said before. And this, the commutator of L and Y k eta is actually of lower order. So what the equation should look like is this YH equals to nu L YH plus lower order terms. And so we use this to, well, we use this in the same sense that I used in the main energy estimates. And hopefully the lower order terms one can try to control. And this is exactly what we can do. So let me just give you the estimate one can prove after combining everything. So what this says is, let's say you flow H at time tau under this flow, Sk, till time t, then what I can get is I can get the new dependent decay for any n. This new dependent decay, but I can also get a new independent decay. This is, well, this is essentially what will give us Landau damping. And what you have to pay is the norm, or is this L2 norm of H commuted with Y. So what's going on here is I just commute with enough Y and use Poincare to get this decay. and use hypocoercivity to get this decay. Does that make sense? Okay, finally, I will use the main energy estimates for Vlasov Poisson Landau to estimate this. So this is how everything ties in together. So I use density estimates to control the E terms and the energy estimates for the main energy estimates, but then I also use the main energy estimates to to feed into the density estimates. And that's why I say we have to prove them in parallel, for example. Are there any questions? If not, then I'm just going to mention a few additional difficulties that I did not talk about. Okay, I did talk about the interplay of Y and L a little bit, but you generate these error terms which are the same order as the dissipation terms. So you need to do there has to be goes some work into taking care of this issue. The second one is the hierarchy of velocity weights, because now you have an additional vector field. You need to also account for that. Finally, proving decay for energy and the density. What we prove is without Y commutations, but since I don't want a loss in nu or t, we occur at top, or that we have at the top order, we need a new idea to actually close the estimate. So a lot of the work goes into this. Okay, so these are the additional difficulties, and let me mention some future directions and problems that we can try to look at. The first one is Vlasov-Poisson-Boltzmann for non-cutoff Boltzmann. So, but now the linear operator is of fractional order, so the new 1/3 scaling should change. So Jacob also mentioned this in his paper. I'm not sure what the scaling is, but it should depend on the singularity. Second of all, one can try to understand the same question for general bounded domains. The issue with our problem, with what we do, is we require very high solar regularity. So this is not very useful for general domains. And Guo's method only gives a low regularity result for data of size ONU. So then it would be interesting to say what one can try to get, let's say in a general bounded domain. Nu 1/3 might not be the right thing, but I'm not sure what is. Okay, the third question one can try to ask is, what if I do the Vlasov Poisson Landau for Gevrey data? For Gevrey data by Muo-Villani or Bedrossian, Masmoudi, and Muo, you know that you can get everything for size O1. So hopefully you can try to prove the same result for size O1 instead of O nu 1/3. Finally, can I actually improve the decay I get to exponential decay or not? It would be interesting to understand if either this is sharp, the exponential or the stretch exponential decay I get is sharp, or if it can be improved. And this is related to understanding the non-degenerate spectral gap that we have for Landau. Okay, thank you. This is the end now.
So thank you, Sanchit. Are there questions?
Yeah, those are really good results, by the way.
Thank you, Jacob.
So I just had a quick question. So I guess when you do the resolvent estimates, you have to do it kind of like uniformly in the collisional parameter nu.
Yeah.
And these must be hard, right? I mean, you don't have a good expression for this k, but you have to somehow basically.
So the point is, yeah.
I mean, you're kind of using the Penrose condition on the Maxwellian, kind of hidden in there.
Yeah.
You no longer have an explicit expression. So this must be hard. Am I right in saying?
I mean, yeah, they're hard, but the point is, you can use the energy estimates again for Landau to actually say something. And so I mean, it's
about the Laplace transform, no? Because you have to do something Laplace transform-esque, right?
Yeah, you have to do everything of that form. Yeah, you have to do everything of that form. Right. I mean, they're hard. I don't think they're much. I mean, they're of course harder than what you would get just for transport or for Vlasov-Poisson, but they're not like that much harder because well, okay, maybe I'm a little biased here, but
right. So you're basically proving that somehow like your kernel for positive nu sort of converges in a good way to the
Yeah.
kernel for regular
Exactly,
new, and then
yeah.
therefore for new small enough, you get good
Yeah.
Laplace transform properties. Like you have that
Right.
that pole condition, whatever. Right?
Yeah, right. That's
You do
exactly what
something
we're
like
doing.
this.
Yeah, yeah.
Smart. Yeah,
Yeah.
it still sounds pretty hard, but yeah.
I mean,
Okay,
yeah.
cool.
So I cannot say that that stuff is as Toan the expert on it. So,
Mhm.
so yeah. So
Yeah.
that seemed to be
Cool. Yeah. No, and there's lots of really interesting aspects of this work. Thanks for the nice talk.
No, thank you.